In this lesson, we're going to be looking at a new way of describing a sequence of numbers. In fact, it's not really a new way. It's probably the first way you would have come across when you first investigated sequences of numbers. Looking for a pattern would have involved looking at how you get one term from the last term. So a sequence that we would now think of as a linear sequence, you would describe as a sequence where you're adding the same thing each time. So the rule would be add 5 or whatever. Often we find that the more complicated a sequence gets, the harder it is to come up with a nice closed form. In other words, a sensible formula that we would understand for an nth term of the sequence. And yet it might still be possible to create some kind of formula that tells us a given term, provided we know the term before, or perhaps the first two terms in the sequence will give us the third, and the second and third will give us the fourth, and so on. We're also going to look at another type of sequence that we can deal with, periodic sequences, sequence of numbers that somehow repeats themselves after a certain length of time. And because of their repetitive nature, we can investigate what happens and calculate things like the sum of however many terms we like by exploiting the fact that we know all the terms in the sequence and we know that they're going to keep coming back to the same set of terms. To begin with, have a quick go at this problem. Think of a number, doesn't matter which, halve it and add 5, and then halve that and add 5, and so on and so forth. You might be able to use your calculator to do this really quickly and easily. Give it a try with whatever number you like and see what you notice. When you're ready, unpause the video and we'll continue. So this is what happened when I tried this with a few different starting values. I'm using the notation U1 to represent the first term, and then U2 as the second term, and so on. If I start with a value 2, halve it and add 5, I get 6. Halve 6 and add 5, I get 8, and so on. Now, I've tried this with a few different starting values, and in almost every case, we get numbers that change every time. In the first case, the numbers are constantly getting bigger, but by smaller and smaller amounts. For the second case, where I started with 12, the numbers are getting smaller, but in smaller and smaller amounts. When I started with -4, it jumped up quite quickly and became positive, and then continued to increase, but in smaller and smaller amounts. 100 shrunk pretty quickly, all the way down to nearly half of itself, and then nearly half again, until that one was also getting close to what looks like some kind of fixed limit. And in fact, a nice way to think about that limit might be that there is a number you can start at where the sequence doesn't increase or decrease. It's kind of like the bottom of a valley or the lowest point of a bowl. Anywhere else you drop a drop of water in the bowl, it's going to flow down to the bottom of the bowl from whichever side you pour it, unless you pour it right in the middle, in which case it's already at the lowest point. We can describe this pattern, the sequence that I've given you, halve it and add 5 is the rule. We can describe that rule by saying that the nth term is always equal to half of the previous term, the n-1th term, plus 5. In order to fully describe a sequence like that, in other words, for you to know exactly what the numbers are that I'm thinking of, I'd have to give you a starting value. So if I say think of a number, I'm basically allowing you to come up with any sequence you like. Whereas if I want to describe a particular sequence, I'd need to tell you the first term is such and such, and the rule is each new term is derived by doing half of the previous term plus 5. Those two things combined uniquely describe the sequence. Remember, if you want to do this on a calculator, a nice quick way to do it is to make use of the answer button. So if you have 0.5 times answer plus 5, and you've got a number in there already from your previous calculations, pressing equals a bunch of times will quickly work you through the process, and you'll be able to see that the results are in fact tending closer and closer to the answer that it seems to be approaching, which is 10. Let's take a look at this way of describing sequences in a bit more detail. In general, we like the idea of having an nth term rule that's just in terms of n, but in some cases that's a little tricky to find. So for instance, if we've got the terms in this sequence 1, 3, 7, 15, 31, we can describe their position, that's just where they are in the sequence, the first term, the second term, the third term, and so on, all the way up to the nth term. But it might be trickier than you think to come up with an nth term rule for this. I'd encourage you to pause and have a think about the sequence. You might be able to work out the next term in the sequence, and then if you understand it a little better, maybe you can describe how to get from one term to the next. but can you work out a way to get from the position to the term itself? Is there a rule that you can say, oh, you want the fourth term, I'll do something with the number 4 and get an answer of 15, or something where I give you the n and you give me the nth term? Okay, here is the rule for this one. The clue is that this sequence is almost but not quite geometric. The terms are, roughly speaking, getting twice as big every time, but it's not as simple as always getting exactly twice as big. The nth term rule happens to be that each number is 1 less than a power of 2. So if you do 2 to the 1, take away 1, then you're going to get 1. 2 squared, take away 1 is 3. 2 cubed, take away 1 is 7, and so on. The recurrence relation might well have been easier for people to spot. If you take the number 3 and double it and then add 1, you get 7. If you double that and add 1, you get 15. Double that and add 1, 31, and so on. So the recurrence relation that describes this actually looks a lot simpler. There's no weird powers, there's no exponential functions in here. It's just double the previous term and add 1. So in general, you might think that a recurrence relation is easier to find, and very often that's the case, especially with sequences that rely not just on the term before, but perhaps the previous 2 terms. The most famous example of this is probably the Fibonacci sequence. So if you've got the first 2 terms being 1 and 1, and then each new term after that will be the sum of the previous 2 terms, then it starts out nice and simple, 1, 1, 2, 3, 5, and then the numbers start to get bigger, faster and faster, in a way that looks kind of geometric, but is a little more complicated even than the previous one that we saw. So the next term is going to be 8 because it's 3 and 5, and the term after that is 13 because it's 5 and 8, and so on. Now, there is an nth term rule for this, and I would be very surprised if any of you have managed to figure it out for yourselves, because, well, it looks a little bit weird. There are reasons behind this. It's possible for people doing A-level further maths, you'll learn how to prove a result like this using induction, and it's just possible that you might learn enough about how matrices work to discover how this formula was derived in the first place. But it is kind of still harking back to the idea of something geometric, because in fact this sequence, although it's not going up in nice scale factor steps like a geometric sequence might be, there is something geometric about it. Roughly speaking, if you graph it, it looks like it's something like 1 plus root 5 over 2 to the power n kind of sequence, but there's a little bit more messiness in there, hence the weird nth term rule. Luckily for us, the recurrence relation is just so much simpler. So if you're wondering whether recurrence relations are just better than nth term rules, not necessarily. They're not as useful perhaps depending on what you want to do, but they're often a lot easier to come up with, and therefore they're going to be quite a common thing to work with if you're dealing with sequences. Let's explore what happens when we're given a recurrence relation and we're asked to use it. Let's start with this rule. The nth term is always a half of the previous term plus 6, and you're going to explore what happens with a few different starting values. Give it a try and see what you notice. Okay, so the idea here is that you can explore not just what happens for your particular sequence, but to see what would happen if you modify the starting conditions. You should find that similar to the initial question we started with, this sequence appears to approach a fixed value. And in fact, we can explore what that fixed value would be by considering a limit that the sequence is approaching. It's a bit of a weird idea, but if you imagine going up not just to a very distant term in the sequence, but to the infinitieth term, if such a thing exists. If you are approaching a limit, then it might make sense to think about the infinitieth term. So a term so far along that you've already reached your limit. And if you've reached the limit, if the term you're looking at is so distant in the sequence that you're effectively at the limiting value, then the term just before is going to be pretty much in the same place. So the trick for calculating the limit is to replace un and un minus 1 with the same letter. Call it L for limit. And in this case, we'd have L equals 0.5L plus 6. And a quick bit of rearranging would show you that you end up with 0.5L equals 6, so L equals 12. And you can explore and investigate what happens. You would have seen when we started with 4, the sequence will gradually get closer and closer to 12, creeping up from below. Minus 10 does the same thing, but if you start with 12, it just stays at 12. It's like a fixed point. Just like we had 10 previously, we've got 12 this time. Half of 12 plus 6 is still 12. If you start with a number bigger than 12, halving and adding 6 will shrink the value, and if you start with a number less than 12, halving and adding 6 will increase the value. But if you start at 12, you stay put. Now, we've got a few different definitions because the next part of this lesson is going to explore different types of sequence. We've got a couple of defining terms for a sequence which is constantly on the rise. So if each new term is greater than the term before, we call it an increasing sequence. You'll occasionally come across this term. And a sequence is called decreasing, sensibly enough, if every new term is lower than the one before. Now, as we've already seen, you can get an increasing sequence that's always increasing and yet never quite gets beyond a particular hard limit. And similarly with a decreasing sequence. I mean, you can think about some of the geometric sequences and series that you've looked at, where perhaps you're halving every single time, or you're multiplying by 0.9, and the terms in the sequence are constantly getting lower, so it's a decreasing sequence, and yet they never quite shrink to nothing, and you could even add them all up and get a sensible answer at the end. So just because a sequence is increasing or decreasing doesn't necessarily tell you much about what it's increasing to or whether it's limited, and it's quite possible that you'll even end up with a sequence which, even though every term is non-zero, the sum might still be a sensible value. The next and more interesting definition is this one of periodic sequences. If the terms repeat in a cycle, we have a periodic sequence. So think about a simple one like 2, 4, 7, 2, 4, 7, 2, 4, 7, and so on. The 2, 4, 7 is in whatever arbitrary pattern it might be, but then that same sequence of numbers just comes back again. So all you need to learn in order to memorize a periodic sequence is the terms within that single repeated pattern, and then you just repeat it over and over again. This is why, although some people spend many years trying to memorize millions of digits of pi, nobody yet has given an award for someone to memorize the digits of a seventh, because all you need to do is learn 6 digits, 1, 4, 2, 8, 5, 7, and then repeat them over and over again until people get bored and leave the room. You can have a go at calculating the 100th digit of a seventh using the periodic sequence that I've given you here. It starts 1, 4, 2, 8, 5, 7, and then begins to repeat those 6 digits over again. U100 will be the 100th term. I'd encourage you to pause and have a think about what technique you could use to work out exactly what number you would end up at if you keep cycling back around those same 6 digits. And then when you've done that, see if you can build on that idea to come up with a clever method for adding up all of the first 100 terms. I encourage you to pause if you haven't and have a go at calculating those, and then unpause when you're ready to see the solutions. Okay, this is what we have for the 100th term of the sequence. You recognize that the repeating pattern is periodic with order 6, which is another way of saying you have 6 terms before we repeat again. And that means that the 6th term is the same as the 12th term and is also the same as the 18th term, and so on. We could say that U1 is equal to U7. The important point is that any term you like is going to be equal to the term which is 6 places further along, or the term which is 6 places before it. And if you're looking for the 100th term, you just have to work out which of those 6 values you're going to hit after you've gone 100 terms in. And a good way to do this is to see how many 6s there are in 100, and most importantly, how many are left over. It'd be like trying to work out what time of day it would be in 100 hours time or something like that. In that case, you'd be dealing with a clock with 12 hours. In this case, we're just looking at a sequence of 6 numbers. So 100 divided by 6 is 16 and a bit, which means you'll get 16 complete cycles, but then you'll get a bit more as well. So we know, for instance, that 16 6s, which is 96, that will be the last term of the first 6 complete cycles. That means we've got number 97, 98, 99, and 100. and that is 4 more terms. So that's going to be the first 4 terms of another set of 6. That takes you through the 1, the 4, the 2, and the 8. If you want to add up that sequence, you use exactly the same idea. You say we've cycled through 16 complete sets of 6. So that's going to be 16 lots of the 1, 4, 2, 8, 5, and 7 added together. And then we also need those additional 4 tacked on the end, the 1, the 4, the 2, and the 8. So you add up the ones that you have in that set of 6, multiply by 16, and you tack on the few remaining ones. There is no fancy formula for this in the way that you might expect for a geometric series or an arithmetic series. There is just common sense and understanding what it means to be a periodic sequence. Next, I'd encourage you to pause and have a go at this exam style question. When you've had a chance to look through and think about it and try for yourself, I'm going to put up a few hints and discuss it a little bit, and we'll talk through exactly how you would solve a problem like this. It's a good example of using recurrence relations and taking advantage of the concept of periodic sequences. Okay, let's have a look at a few hints. First of all, you're told that the sequence is defined as un plus 1 is equal to k over 1 minus un, which means if you know one of the terms, then you'll be doing something divided by 1 minus whichever term you're on in order to calculate the next term. What they haven't done is give you the constant k that should be on top of the fraction. So you know there is some number, we just don't know what it is, which is why they've given us a couple of hints. So first of all, they've told you the sequence is periodic and it has order 3. Order 3 means if you move 1, 2, 3 places along, then you'll be at exactly the same number you were at before. In particular, that means the 4th term will be equal to the 1st term. In other words, terms 1, 2, and 3 might be all different to each other, but then terms 4, 5, and 6 are the same as terms 1, 2, and 3. And the same will happen again further along, should it become necessary to look that far. They also give you the 1st term, so we know where we're starting. The first thing I would do here is substitute that value into the expression you're given, so you can find a new expression for u2. But that expression is going to involve k, because we don't know what k is yet. Once you've got that value, sub it in again, and you'll be able to calculate u3, again in terms of k. And finally, sub it in one more time, and you'll be able to find an expression for u4, and this is where you can stop, because you know that u4 is definitely equal to u1. It's a periodic sequence, so the 4th term and the 1st term have to be the same if it's a periodic sequence of order 3. And this is a really important point. Simplify as much as possible at each step. If you just throw each new expression unsimplified into the fraction, you're going to get a fraction within a fraction, and then for the next step, a fraction within a fraction within a fraction, and so on. So if you don't want to be left with lots and lots of messy fractions to work with at the very end, then do as much simplifying as you can as you go along. Anytime you discover a fraction inside a fraction, well, multiply top and bottom of the main fraction by any awkward denominators and reduce the thing to its simplest form before you sub it into the next step. Now, in part B, after you've presumably solved the quadratic equation, I'm guessing that k equals minus 12 will be one of your solutions. And I suppose that must mean that the other solution is the valid one. But they're asking you to explain why k equals minus 12 is not a valid solution. And that's a little bit subtle. You'll have to think about what would happen if k was minus 12. Think of it a bit like a proof by contradiction. You've got 2 possible values for k, and they're asking you to justify why minus 12 wouldn't work. Well, go back, substitute it in, and see what you notice. And then maybe try substituting in your other value and check that it gives you exactly what you're expecting. You have to think a little carefully about the definition of a periodic sequence of order 3 for this bit. And then for the final part, remember your summation notation. R equals 1 to 50 just means you're going to go through 50 times looking at UR, where R takes values of 1, 2, 3, and so on, all the way up to 50. It's just a fancy way of saying U1 plus U2 plus U3, and so on, all the way up to U50, the 50th term. Now, if you know that you want the sum of the first 50 terms of the sequence, and you know it's a periodic sequence of order 3, and you've already calculated the value of k, you've even subbed it back in so you know what your numbers are, then you can use the same trick we used previously to think about what the sum of the 3 terms are in this repetitive sequence, then how many groups of 3 you'll have if you're adding up 50 such terms, and what will be left over at the end. So I'd encourage you to give that a proper go and work through it for yourself. Hopefully, once you get to the end, you'll be able to check that it works. And if you want additional confirmation, well, you could use a calculator or try plugging this into a spreadsheet to see if the numbers really do follow the pattern they're supposed to. That's how you know you've got it right. There's a few more questions that you might find helpful to try from the textbook, from exercise 3G and 3H. They will involve periodic sequences and recurrence relations, and sometimes your recurrence relations will produce something to do with limits, like in question 2 here, and sometimes they'll be looking for an understanding of how a periodic sequence works in order to calculate a sum, like in question 1. So you could have a go at the questions from the book, and you can have a go at these bonus problems as well, if you like. This final section is going to be a bit of a bonus that links to trigonometry. So we now have, given that you've studied chapter 6 from the year 2 book, we have knowledge of a few additional trig functions, and that makes it a little bit easier to work with things like the reciprocal of sine or cos. We're going to use a recurrence relation that is a little bit like Fibonacci in the sense that you need the previous 2 terms to compute the current term. So I've set this up as un plus 2 is equal to un plus 1 divided by un. In other words, the term I want is going to be the term immediately before divided by the term immediately before that. So for instance, u3 is going to be calculated by doing u2 divided by u1. In this particular case, u1 and u2 are provided for you, but they're given in terms of theta, which is why the question has asked you for expressions in terms of theta for u3 and u4. And then the next part asks you to demonstrate that the sequence is in fact periodic, which means calculating enough terms that you can see that it eventually repeats. And state the period means you're going to say how often it repeats itself. So in other words, how many terms you have to go through until you get back to the start. And the final part, you're going to be substituting in theta equals pi by 6. So that will give you specific values for all of the terms that you've calculated. And you'll be able to use your understanding of how periodic sequences work to calculate an actual value for the sum from 1 to 30. Pause and have a go at this question, and then I'll show you some solutions. So for this first part, if you divide the second term by the first term, you get something that simplifies to tan theta. If you then divide the third term by the second term, you can get the fourth term. Tan divided by sine can definitely be simplified. In fact, the best way to do it is to reduce tan to its more fundamental format, sine theta over cos theta. Because we're dividing by sine theta, we end up getting just 1 over cos theta. A nice way to think of this is that that fraction with a sine over cos on the top and just sine theta on the bottom, we could multiply the top and the bottom of that fraction by cos theta. And on the top, that would just give you sine theta because the cos theta cancels out. On the bottom, you get sine theta times cos theta. But then you've got sine theta on the top and the bottom. So that would cancel because you can divide top and bottom both by sine theta, and you're left with just 1 over cos theta, which is, of course, sec theta. Now, in order to prove the sequence is periodic, you'd have to calculate a few more terms. So here we've got u5 calculated in the same way, and you'd have to break that apart into sines and coses perhaps to demonstrate or convince yourself that you get cosec, but it should work. And a similar thing will show you that the next term in the sequence is cot theta. You still have to go a little bit further because we're trying to prove that the sequence is periodic. And now we've got back to cos theta, you might be thinking your work is done. But be a little bit careful. This reminds me of the occasional recurring decimal, when if you're trying to divide something by 17, you'll find that the recurring decimal expansion is something like 16 digits long. Well, it's not possible to have 16 digits that are all different because there are only 10 digits, which means there must be points in that sequence of numbers where the same digit appears. But that doesn't automatically mean it repeats at that point. It doesn't repeat until after it's done 16 digits. And it's similar with this. We can't be sure that we've reached a point where everything's going to repeat because this particular recurrence relation relies on two starting values in order to calculate the next value. So we've got to go a little step further and demonstrate that now we've got back to a point where we have cos and sine, and therefore the next term we get is obviously going to have to be the same as what we got for u3. And that will be sufficient to prove that it's periodic. We now know that u7 is the same as u1, u8 is the same as u2, and that justifies the claim that the sequence has an order 6 period. The next bit just involves substituting pi by 6 into each of these terms, which is a bit tedious, but the numbers are all quite nice because everything either involves sine of pi by 6, which is a half, or cos of pi by 6, which is root 3 over 2, or reciprocals of those. And it's possible, I suppose, to go right back to the beginning, replace cos theta and sine theta with root 3 over 2 and a half, and then rederive all of the other terms directly from that. And that might be just as quick as substituting it into the trigonometric form that I've got here. The trick is to recognize that because the sequence is periodic with order 6, we just need all 6 of those terms, and then another 6, then another 6, and then a couple more, because 30 divides exactly by 6. So we just have 5 complete groups of those terms. We can add up those terms, rationalize some denominators, simplify things, combine stuff, and we end up with exactly 25 over 2 multiplied by 1 plus root 3, which you can write in a few different ways. This is about as simple as it gets. So that's a combination of trigonometry and recurrence relations, and it gives you a good idea of the kinds of skills that you'd be expected to demonstrate in the exam.